The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So I'd like to welcome our next speaker, and that's Jose Sanchez. And Jose is a master's student working with Professor Nakin, that many of us know, at Concordia in Canada. Welcome.
Good morning, everyone. It's a great honor to be here, first time. Our work, Evaluation of Saturation Technique for in situ surface electrical resistivity measurement by Dr. Michel Nakin and Jose Sanchez with me, Concordia University, Montreal, Canada. This is the agenda: resistivity, saturation effect, objective, mixture design, experimental program, observation, conclusion, and recommendation. I'm just going to fly through the first 10 slides. Thank you, because the previous the person who was here, he made an excellent background, so I don't need to explain so much. Resistivity, just a basic one, is like as a property that describes how difficult it is for the electrical current pass through a material, in this case, concrete. This is a very rough and simple resistivity background. We can say like you start with the federal highways, the applicability of resistivity in concrete. And since then, many improvements and updates have been done. And this is the method that are currently available, the RCPT test. And for this research, we are using the PROSEC, the 104 proof. But we need to ask, like, why electrical resistivity is related to permeability. It's quite simple. If you can see this picture, you are going to have two kinds of network, connected and not connected. When you have a connected, for the electron, when you apply a voltage to the concrete, the electron are going to have it's going to be easy for them to move to the disconnected network, and it's the same for the water. With the chlorides and sulfides, they are going to move easily. And when you don't have a not connected, it's because you are going to have a less permeable concrete, and you are going to have a high resistivity. According to previous research, what we have is like when you are using supplementary cementitious material, you are going to have for sure a refined network, a more complex, so you are going to have a higher resistivity. And also when you increase the water cement ratio, you are going to have a less complex structure. So it's going to be simple for the electron to pass through the material. These are some factors that influence resistivity. I know that we don't see here rebars or something, but for this presentation, we are only going to focus on saturation. We know that the effect of saturation is very simple. If you don't saturate the sample, you are going to obtain a zero value. So the question right now is like how much time require the sample in the lab or in the field be saturated, 1 hour, 3 hours, 3 days. So this is something that is going to be in our objective, is understand the influence of saturation in the field or in the lab samples. Also, one of the other second objective is investigate the difference between geometry samples, slabs, cylinders, cores, and structures. And the final and the main goal of this research, sorry, I forgot to mention, this is a work in progress research that we start in the winter of, in a lovely winter of Montreal. So the final goal from this research is to develop an adequate method to saturate in the field and obtain a reliable value of resistivity of of resistivity. These are the mixture design that we have. The first one is 100 Ti, that means 100 Portland cement. Then the last four are a combination between Portland cement and supplementary cementitious material like slag and fly ash. And also we use the third one is limestone with a slag, only to see how the port network change. And I am not going to go through in detail with this. I can explain later. The experimental program was like we cast all these 100 cylinders with different mixes. Also, I forgot to mention, like you can see the water cement, we start like the design are 0.4, 0.5, and 0.6. So we cast, for the first 7 days, we stored these samples in lime water according to the AASHTO standard procedure. And after that, we remove the sample and we measure for 3 days at different times, different hours. So we start like, okay, what happened when you put the sample in 1 hour condition, in 1 hour saturation? What happened 3, 6, 24, 48, 72? So we obtain something like that from all these samples. You can see when you have 100 Portland cement at 20 days, the behavior that they have. You can see this graphic, saturation against surface resistivity. At the first 6 hours, you can see how it moves. You can see two things here. After 24 hours, you are going to obtain a stable behavior. And also, the difference between the first value, that was like only 1 hour, and 72 hours of saturation, the difference is only 9.5%, the difference between these 2 points. With the other sample, with this mix that is 50% Portland cement, 20% fly ash, and 30% slag, you have a different kind of behavior, but the difference here between the first one that was only 1 hour and 72 hours is just 3.5. This mixture is 50% limestone and 50% slag, and the behavior is quite similar to the first one, but the important here is like if you compare the first one at 28 days, if you compare the resistivity obtained during the first hour of saturation and 72 hours, is only 2.2%. The average of all these samples, like the water cement was 0.3, 5, and 5. At 91 days, the behavior, like they remain. 100% cement, you can see like after 24 hours is quite enough time to saturate completely the sample. And the difference between the first measurement and the last one is just only 8%. For the second one, it's just 6.5. For this sample that is limestone and with a slag, it's only 1.7. So 3 kind of different behavior was observed during 28 days, 56 days, but I didn't include it, and 91 days. Also, we were start thinking like, okay, we are going to have all these same behavior with different geometry. So we decide to use a slab, circular slab. Sorry, I forgot to mention this. It's very important. We compare also the mixes, like all the point with a water cement of 0.4 at 28 days and 91 days. So you can see here 2 important things. The first one is when we are comparing the first value at 1 hour and 24 hours saturation and 72 hours of saturation. You can see like the resistivity is almost quite similar, only 2% different. And also another thing very important here is you can see the difference between 100, using just mixes with 100 Portland cement, and how the resistivity increase when you are using a slag or any other supplementary cementation is almost more than 6 times the value that you are going to obtain. At 91 days, the difference between the resistivity is only 3%. With the mixes with a 0.5 water cement, also the difference between every time that we measure is very small, 2%, and 91 days 7%, 0.6 also 2 and 3%. And this is something that we observed that was very interesting for us. As you would expect when you import cement, when you increase the water cement ratio, it is expected that resistivity is going to decrease, yeah, because you are affecting the network. But we observed that when you are using a slag, or especially slag, it didn't happen. You can see here like 0.4 and an increase in 0.5, and 0.6 is quite similar. Also, we observed this in this other mixture. So it seems that when you are using supplementary cementitious material like slag, you are going to have a very complex network, but it's not going to affect by the increasing the water cement. Now about the slab, sorry about that. We were thinking like, okay, we are going to have the same behavior with circular slab, so we decide to cast some samples with a water cement equal to 0.4 to see what happened. And also we want to, based on launch 2008, we installed some sensor in order to understand how the humidity change inside the concrete. So this is a picture of the slab, and also it describes the location of the sensor. You can see like we put it like every 20, 40, 65, 95 millimeters depth, and it was like a test to understand how it's going to change. Okay, but with the geometry result, the behavior is quite similar, but although we applied this correlation factor, the slab was 30% less than the cylinder sample. For the other mixture design, it was observed again that the slab was 17% less. 56 days, the same. It was a constant behavior. The slab is going to have always a less resistivity value in comparison with the other. With the sensor, we didn't obtain any positive result. Nothing happened, to be honest. The sensors were there for 1 hour, 6 hours, 72 hours, and we think like the issue was like the sensor were like the distance between every sensor was too high. So we are rethinking on doing and changing the location to put it like closer. Also, we test old samples that they were stored in the lab in standard condition. So in the lab, you kind of have like a 50% humidity condition during 5 years. So it's quite similar that something that you are going to obtain maybe in the field. So we said like, okay, and also we asked to ourselves like, how much time you need to obtain a first value, a first resistivity value. So we start this testing on this sample, 75% Portland cement and 20% fly ash. For the first hour, we start obtaining the first resistivity value after just 5 minutes. For the first hour, every 7 minutes, we start measuring, and you can see here that this is the first hour, and it was a decrease in 80%. So the saturation is a big issue. Also, the complete test was 72 hours, and you can see this line represent the first hour, and until 72 hours, you can see that after 24 hours, you obtain almost a constant behavior. This is quite similar with the other mix, the old sample. The first hour how decrease 12%. And when you are taking the old test graphic, you can see that after 24 hours, it's enough time to saturate, according to this. So we use this test because if places like maybe Phoenix that the humidity is like 50%, we should expect something maybe in the field with this, similar to this. Observation that we have until now is that when you are using this device, the waterproof proof, the samples in the lab require a lime water solution or 100 humidity. So this is, you are not going to find this in the field in the real life. Also, when you storage in lime water, maybe the samples are going to have an additional curing and leaching and all the things that my previous colleague explained. So this is not how the real structure in the field is going to behave. So until now, we have some conclusion for this 6-month work, that saturation can be accomplished only after in the lab for just only 24 hours is enough time. The difference observed, there are different between cylinders and slab, although we apply the correlation factor. Tap water is as good as a lime water solution. However, we want to focus on this recommendation to the future and to finish this project is besides thinking in fully saturation, is important to start thinking on partially saturated elements in order to be able to do this like in the field. And also, another approach is develop an adequate method to saturate in the field. So according to this, if we start thinking in partially saturated elements, we can use this following expression by Weiss. He developed this year. I think that he's coming, like I don't know, I think that is the last one to explain. Okay, so I'm going to meet him. And the basic idea is like using this expression, partially saturate, you can, all these terms are related to the port network and the degree of saturation that you have until this moment. So it will be a new approach, and perhaps he is going to explain in a better way this. And also an in situ saturation method. Oh, yeah. Okay, good. We start with the base of Resol Moreno, who is going to be next to me, like next after me. And he started using a container attached to a concrete element. So he left this container for several days, and he found that there is a correlation between when you test these directly and when you have core drill samples. But the thing that we want to improve in this is like using the same principle that has the German water permeation test, the GWT, that is like we want to use a plate and make a vacuum to attach them to the element, and then pressure the water in order to obtain a rapid saturation. And with these tables that are developed by one of my colleagues at Concordia, Montreal, we can understand, we can know how the deep of the water, how deep the water is going in the concrete. And this is more like, we really believe that using this new two, these two approach, we are going to be more close to the field, because that's the main goal of resistivity. So thank you so much for the time and patience.
Okay, thank you.
Question?